Gone. Life is fun. All right. So physics 2, it's an artifact of history that we do physics 1 first, and then we do physics 2 second. Now, what happens with physics, you've got to remember that mathematics all derives from physics. So in physics 1, we focus on mechanics. And even though last semester, for those of you who had any last semester, we actually got a little bit into thermodynamics, which is great. And mechanics was really about looking at velocity. We introduced forces. We have acceleration. We have rotational motion. And then we got into things that were a little more complex, like fluids. So in physics 2, we're going to take on a lot of different ideas. In physics 2, we're going to deal with waves. And we're going to deal both with mechanical waves and electromagnetic waves. Okay. We're going to deal with electricity. And we're going to get into magnetism. And we're going to finally end up with optics. Now, in some institutions, they will do these mechanical waves as part of mechanics. And the reason being is because one of our examples of waves and how we deal with our waves comes from our idea of the spring. So let's kind of go back and let's look at a spring here. So it's been a while. We've all slept. Many of us have been sick over the break or are currently fighting lovely stuff right now. And we have a spring, and our initial spring length was L0. And we know what happens when we put a weight on the spring. And we put a weight on the spring will stretch. We'll get a stretch. And that stretch we called X, and that's our new length minus the original length. Now, when I play with a spring, if I'm in equilibrium, this is just going to hang down. And remember, when we're hanging something down, we're applying a force. And we use that force here is equal to the weight that we have on our spring. And that was just our mass times gravity. And then we had something that we called Hooke's law. And Hooke's law gave us something that looked like this. We have our spring. We have this. We have our force was equal to minus kx, where this was my stretch. This was the property of my spring. And this is related to the weight. Now, this negative comes from the fact that this wants to restore itself to the original position. Okay, it wants to pull this back up. So basically what's happening is here's my weight, but my spring really wants to pull it back up. And so we've got that negative here because my spring is trying to get a restoring force. So if we put a weight on here and we say that this is a 50-gram weight or 0.05 kilograms, and we say that my stretch is 0.15 meters, we can determine my spring constant. The magnitude of the spring constant is just going to be the force divided by the stretch. And we've got our 0.050 kilograms times gravity, 9.81 meters per second squared, divided by our stretch, which is 0.15 meters. And we can determine that. And give me a second, I'm going to take out my calculator. Gives me 3.27 Newton meters. And we can determine this spring constant for my system. Okay, so far, nothing new. And you're going, all right, what has this got to do with where we're headed in physics 2? Well, this only works when my weight sits there because we know what happens, right? I can take my spring and I can push it down. And then we know what's going to happen is my spring is going to bob up and down, right? We know we get that bobbing up and down. That's kind of an interesting thing. If I were to put a marker, so I've got a piece of paper, my spring will actually bob up and down and my marker is going to do this. Right? So as my spring bobs up and down, and I'm taking a piece of paper, I'm going to get something that bobs up and down like this. And we can represent this as a wave. Right? We see them on water. We see them a variety of different places, and we can call that a wave. Let's look at some characteristics of our wave. So I'm going to draw my wave. And if I'm dealing with the bobbing, okay, if I'm dealing with the bobbing, it's going up and down here. So we're going to say a Y direction. And this is time. So as my spring bobs up and down, I've got this time. Now we've seen waves before, but we want to define some things. We're going to define this. A is going to be my amplitude. And that's how tall the wave is. Okay. That's how tall the wave is. if I go from point to point, that's going to be my wavelength. If I'm in position, because I could do this both position versus time. But if I'm looking at the distance between these two, like in a water wave, that is going to be my wavelength. So we're going to use this lovely lambda as wavelength. And that's for when I'm in position. If I'm in time, the time that it takes to go here and this is to make one complete cycle. That's the period. And then the frequency is 1 over the period. So my amplitude is going to be some sort of length measurement. My wavelength is going to be some sort of length measurement. My period is in seconds, and my frequency is in 1 over seconds, and that gives us a lovely unit of hertz. And we've seen these before, okay? Many of you have taken general chemistry, and we've seen that before. The other thing is, if we remember that velocity is equal to a change in position over a change in time, my velocity of a wave, if I am following a bead on this, my velocity of my wave is going to be my wavelength divided by the period, or my wavelength times my frequency, and this gives me meters per second, and this gives me meters per second. Now, if I were in chemistry, we know what that velocity is, because if it's an electromagnetic wave, they travel at the speed of light. So that becomes C is equal to lambda times my frequency. And sometimes you would have seen this as lambda, depending on your chemistry book, you might have seen it like that. But we're going to use F in here in physics. Now let's think about this wave. We're going to go ahead and look at our wave again. And we're going to think about a wave traveling down a string. So if I have a string and I send a pulse down my string, this wave is going to go down the string. It's going to move, all right? My wave is going to go move down the string, and we've seen that pulse. We've seen it if I'm doing ropes or if I'm doing something, we get this pulse that goes through. So we can talk about that as a pulse. But if I get a standing wave, which we'll come back to, my standing wave is going to look like this. So think of a guitar string, right? Think of something that's got going here. So I have a wave that I can draw that looks like that. Now, waves that look like this are called transverse waves. because they're going to be traveling up and down. We have another kind of wave that we deal with, and when we get to sound, and those are called longitudinal waves. And what's going to happen there is, if you think of a speaker, and as my speaker moves, I get this pulse, and I am going to get a dense section of wave, and then a light section of wave, and then a dense section of wave, and a light section of wave, and a dense section of wave, and a light section of wave, and a dense section of wave, and a light section of wave. What's fun is that slinkies can show you both kinds. This kind of a wave, you think about a string going up and down, or you think about a wave going up and down. This one, you think about a pulse traveling through a slinky that goes like this. So we have lots of different things that we can play with when we're dealing with waves. Okay, so where we started with this is looking at my spring, because what's happening with my spring is, as my spring bobs up and down, it's going to do that. Now, there are lots of systems that are going to have this kind of bobbing type behavior. Think of a pendulum. If I have a pendulum, my pendulum goes to one side and comes back here. So if I'm using my marker at the bottom of the pendulum, guess what happens? I'm going to get something that looks like this. That's one thing. Now let's look at a bead on a circle. If my bead is traveling on my circle, and I'm looking at its position in the Y direction as it goes around, I'm also going to get something that looks like this. I also, on a circle, will get something that looks like this, because I'm looking at the Y direction, or I'm looking at the X direction. So my bobbing spring, my pendulum, something that's traveling around in a circle, tip of a fan blade, a minute hand, all of those things are what are in what we call simple harmonic motion. They're all in simple harmonic motion. And we use the H or the SHM to represent simple harmonic motion. So this behavior, and there are tons of examples. In fact, one of your homework problems is going to be, our homework is to actually send in a video of something in simple harmonic motion. And I'll post that out, and we'll get that in by the end of next week. But I want you to kind of look around and see where you might see simple harmonic motion, because it's all over. I mean, you've got them in your house. I told you about one, the minute hand on your clock, or the second hand on your clock. That's in simple harmonic motion. A ceiling fan is in simple harmonic motion. The fan blades on a turbine are simple harmonic motion. The things that are happening on your wheel, that on your car, looking at the motion of that P, that's simple harmonic motion. This spring representation works out really, really well, because we can represent bonds in chemistry as springs, and they're going to be in simple harmonic motion. So simple harmonic motion is all around us, totally all around us. but that gives you some interesting things to think about. Because let's look at this again. We've got something that represents this motion. We've seen this before. If I were to plot and look at this plot on a graph, I can represent that mathematically. I can totally represent that mathematically. This is either a sine function or it's a cosine function. Because both the sine function and my cosine function will give me the same thing, will give me this behavior. And we got to remember that basically the sine function and the cosine function are just out of phase with each other. Because if I'm looking at the sine of 0, if I'm starting here at 0, the sine of 0 is equal to 0. The cosine of 90 is equal to 0. So basically, the sine of an angle is equal to the cosine of an angle plus 90 degrees. This is a trig identity. Some other things we know about the sine and cosine function is my sine and cosine functions the maximum of those functions is equal to 1, and the minimum is equal to -1. So if I'm drawing my curve here, that's a sine and a cosine. This is really just going from -1 to +1. If I'm just looking at my sine and my cosine function. And that gets back to this unit circle. Gets us back to that unit circle. So I can look at my circle because that's where my sine and my cosine are coming from. And my unit circle, whereas this is 1 and this is -1, or this is 1 or -1 and this is 1. I just have my unit circle and I'm playing with that. So if I've got a bead that's traveling around my circle here, or I have my bobbing spring, I'm just going between this 1 and -1. So that's why we say that the amplitude is going to give me the height of my wave. So I'm going to have an A cosine of an angle, or I'm going to have an A sine of an angle, depending on how I want to set it up. And I can look at the amplitude just by reading off my equation. Just by coming out there and reading off my equation. So I'm going to switch over here for a second. So in here is your simple harmonic motion. So there is something that's bobbing up and down as the wave is traveling through. And you can see that it's just moving up and down as you're going back and forth. So that is one representation of simple harmonic motion. This looks at the simple harmonic motion of a spring. So as I'm bobbing up and down, there's the mass of the spring. It's coming down, it's reaching its maximum point away, it's going back up, it's reaching its minimum point and its maximum point as we're going through time. Here we go, looking at the comparison of the bobbing up and down and going out in around the unit circle. So you can see how we're still getting the same motion as things are bobbing and going back and forth. This is a PDF describing what we're talking about in terms of simple harmonic motion. So this gives you good notes for dealing with the amplitude. We've got our mass on our spring going back and forth. Now, this is giving it to you in terms of calculus, but don't sweat it, right? Don't sweat it, because we're going to use these same equations down here. You just don't have to worry about this part. But here is our position of our object is going to be defined as our position at any time t is going to equal our amplitude cosine of the angle times my angular frequency times time plus whatever phase angle. And that phase angle just tells you where we're going to start. So you've got some nice notes here, and don't get too concerned. But now you can see where we're at in terms of our circle, how things will move just outside of the phase. And we'll get into the kinetic energy and the potential energy of that as we go forward. But you've got some notes there as well. So that's one just extra information. But this gives you the idea of how things are moving. Up in here, oops. I have some lecture notes so that you have our Hooke's law, our simple harmonic motion equations, some of the characteristics of simple harmonic motion. These are going to be our equations of motion for simple harmonic motion. So you actually have a set of notes for this. We've got a set of notes. So you do have that there. I think I've got another set of notes in here. Yep. This also looks at it when we've got things with tension in the string. So as we get to this going forward, you've got another set of notes. So you've got some notes in here that get you that idea of our equations. So I'm going to go back here. I'm losing my voice. It's going to be a long day. All right. Oh. So we're going to use this idea that the position of our spring, of our bead, or anything else is going to be represented by this equation. Where omega is going to equal 2 pi times the frequency, or 2 pi over the period. So this is our angular frequency. A is going to be our amplitude. B is the phase angle. T is time. And X is position. So if I were doing an experiment, this is 7 centimeters. Is minus 7 centimeters. We're going to start up here. We're going to say that this is 5 seconds. So we've got a spring that's bouncing up and down, and we've recorded its motion. It's made a complete cycle at 5 seconds. It's bouncing between a minus 7 centimeters and 7 meters, or 7 centimeters. We want to write the equation of motion. That just means we want to know its position at any time t. So at t is equal to 0, the position is equal to 7 centimeters. Which means if we're using our equation here, it means that the cosine of omega t plus phi has got to equal 1. And the cosine of 0 is equal to 1. T is equal to 0, so that's 0. That means my phase angle is equal to 0. Because that's just telling me that where I'm starting. Okay, that's just telling me where I'm starting, because my amplitude is my maximum stop here. We know that A, just reading it off of my graph, my A is going to be 7 centimeters. That's my amplitude. My phase angle is 0. So my phase angle is going to be 0. My position, my amplitude is going to be 7 centimeters. My period is 5 seconds because it goes from here to here, one complete cycle for my period. So my period T is going to equal 5 seconds, which means my frequency is going to be 1 over 5 or 0.2 hertz. So we can take that graph just by looking at the information on the graph. We know that we're at 7 centimeters. My cosine is going to be omega is going to equal 2 pi over the period, which is going to be 2 pi over 5, which is going to be 2 divided by 5. It's going to be 0.4 pi plus my 0 for my phase angle. And that is my equation of motion. So I can rewrite that. Oops, I forgot a T. Now, WebAssign may ask us, where am I? What is the X when time is equal to let's do at 4 seconds. Okay, so I'm going to be really cool. I'm going to go in here and I'm going to plug it in. Because there's a 0 there. So now I've got 0.4 times 4 times pi. I got a number that looks kind of like this. I got the cosine of 5.03. And if I plug this into my calculator and we say this is degrees, we're going to get a big red X. It's not going to be correct. When we are working with omega, and we're working with our units in terms of pi, we need to be in radians. We're going to be working in radians. So my circle, one complete cycle is equal to 2 pi radians. So you're going to want to verify that you're in radians. If I'm in degrees, I punch this number in degrees in my Blackboard. Blackboard is going to get really persnickety on me and say that is not the right answer. If I am in my radians and I do that, so I've got to shift my calculator. So I'm going to shift my calculator from degrees. Oops, gotta do, okay. Go back, so, enter. I'm going to be in radians. So I'm going to do my cosine 5.03. I get my 0.32, I'm times 7 centimeters. And my position is going to be at 0.04. Oops, I didn't do that right. Try that again. Cosine 5.03 times 7. I'm going to be a position of 2.19. If I go over here to my graph and I look at about where 4 is, so this is going to be 2.5. So 3 is about here, 4 is about there. Yeah, that looks about right on my graph. So you can do it the other way too. So let's give ourselves an equation of motion. I'm going to give x of t is equal to, we're going to do 5 centimeters cosine pi over 2t. So we want to plot this. So I'm going to need my graph. I'm going to do 5 centimeters up, 5 centimeters down. We know we're here. I'm going to go ahead and do this as 1 second, 2 seconds. Oops. I want that to be 2 seconds. This to be 3 seconds. 4 seconds, 5 seconds, 6 seconds. So I'm going to do my pi over 2. So I'm going to do cosine pi divided by 2. Well, at 0 seconds, it's up here. At 1 second, it's pi over 2. So we're good there. Times 5. I'm at 0. At cosine of pi, it would be my 2 seconds. I'm at -1. I'm there. And then I go up here. I'm going to, at 3, I'm going to be there. At 4, I'm going to be at 2 pi. So my curve is going to look like this. So my curve is going to be like this. I can read the amplitude. The amplitude is 5 because this is my amplitude. This omega is going to be pi over 2. And we know that that's equal to 2 pi times the frequency. And it's equal to 2 pi over the period. So I can find the period. Good. So I get t pi divided by 2 is equal to 2 pi. Pi's will cancel out. So t is equal to 4 seconds. And then the frequency is 1 over t, so it's 1 over 4, or it's going to be 0.25 hertz. So whether I'm given the plot or my equation, I can find out an awful lot about the system that I'm working with. And I'm going to stop there for today.